Capacity testing is a proven way to determine the remaining useful life of a battery. But excessive capacity testing can shorten the life of the battery. For this reason, capacity testing is only done about every 5 years. Between capacity tests, the remaining life of the battery can be assessed with impedance testing. This last part of the program will describe battery impedance testing. The key points that will be covered include the purpose of battery impedance testing, the components of an impedance test set, the basic steps for performing the test, and evaluating the test results. The purpose of battery impedance testing is to assess cell condition and the remaining life of a battery while the battery stays in service. The value of measuring cell impedances is based on the principle that cell impedances increase as the battery's capacity decreases. This chart shows a typical curve of cell impedance over the life of the cell. During the first year or two, cell impedance varies some and finally settles to a baseline value. Then the impedance slowly rises as the cell ages and the plates sulfate from use. In the final stages of the cell's rated life, cell impedance increases dramatically over a relatively short period of time as the cell rapidly loses capacity. A cell that ages and loses capacity prematurely will show a rapid increase in impedance during the earliest stages of its rated life. As with any other work done on a battery, all the required safety equipment should be worn and all safe working practices should be followed during the impedance testing. In addition, the battery charger should be in the float mode and should be supplying current to the DC loads. The battery should not be discharging. One component of the test set used to measure impedance is the transmitter. The transmitter generates a low-frequency AC current. A second component is the source leads, which are used to apply the AC current from the transmitter to the battery. The transmitter should be switched off when the source lead connections are made. The leads are first connected to the transmitter and then to the negative terminal on the last cell of the battery and to the positive terminal on the first cell. After the source leads are connected, the transmitter is plugged into a standard AC outlet and switched on. A third component of the test set is the receiver. Jaws on the receiver are clamped around an intercell connector or an inter-tier connector. The receiver then measures the AC current flowing through the battery. Voltage probes connected to the receiver are placed firmly across the terminals of the cell being tested. The receiver then also measures the AC voltage across the cell. The receiver uses the AC current and AC voltage values to internally compute the cell impedance. It then displays the impedance in milliohms. The impedance is recorded on the battery impedance data form provided with the test equipment or on your company's specific test form. The impedance of each cell in the battery is checked in the same manner by simply moving the voltage probes from the terminals of one cell to another. In addition to checking cell impedance, the impedance of intercell connections can also be checked by placing the voltage probes across the terminals of adjacent cells. After the impedance tests are completed, the receiver is removed from the battery and the transmitter is turned off. Then the source leads can be removed from the battery. To avoid the possibility of arcing, the source leads should be removed only after the transmitter has been turned off. The impedance measurements can be interpreted for individual cell condition and for remaining cell life expectancy. To evaluate cell condition, the cell impedances for the entire battery are averaged. Then the individual cell impedances are compared with the average. If cell impedances vary by more than plus or minus 20% from the average, the battery may need to be put on an equalizing charge. Or the questionable cells may need to be capacity tested. Each cell impedance can also be charted with previous readings for the cell and compared to the normal cell impedance life curve. If there's a rapid increase in impedance, the cell or the entire battery may need to be replaced, depending on the age of the battery. The same historical comparisons can also be made for the impedances of intercell connections. Connection impedance is similar to connection resistance, although they cannot be directly compared. Connections showing significant increases in impedance may need to be thoroughly cleaned to reduce the impedance.